My name is Mahatta Oza. I am lecturer in Atmiya Institute of Technology from Rajkot, and today we will learn about the chapter number 5th, superconductivity. Now first we learn about discovery of the superconductivity. Superconductivity was found by the Hayek Kamerlingh once. He is the Dutch scientist in 1911. Now, what is superconductivity? It means definition. Superconductivity is the flow of electric current without any resistance, certain metals, alloys and ceramics at temperatures near about absolutely zero. It is called superconductivity. Now the introduction of superconductivity. Generally, resistivity is linearly increasing with the temperature near about room temperature. But in superconducting material, the resistivity is non-linearly decreases with the temperature. Now, in helium gas was liquefied at 4.2 Kelvin liquefied at 4.2 Kelvin by Kamerlingh once is found out in 1908. Now, liquid helium has a temperature near about 4.2 Kelvin. The properties of mercury at very low temperatures and its also temperature is near about 4.2 Kelvin. He found that the resistivity mercury suddenly dropped to 0 at 4.2 Kelvin and it is called the critical temperature. Now what is critical temperature? Critical temperature, it means that resistivity of the material is suddenly dropped to 0. Below resistivity dropped to 0, it is called superconducting material, and above this it is called to normal conducting materials. At 4.2 Kelvin, the resistivity of mercury in the order of 10 raised to minus 5, that near about temperature in 4.2 Kelvin. Mercury is converted into superconducting material from to normal material. From a normal conductor, the relation between temperature and resistivity, here shows a graph, temperature versus resistivity. Here Tc is the resistivity is near becomes to 0 and this material is superconducting material and this state material is becoming like a normal temperature. At very low temperature, a normal conductor has some resistivity, but for a superconducting material the resistivity is suddenly dropped to 0 at very low temperature. Now the properties of superconducting material. General properties of superconducting material is the electrical resistivity. Second thing, Meissner effect, magnetic flux line are explored. There is discontinuous changes in the specific heat and many other properties of superconducting material. Now first property is the electrical resistance. The electrical resistance of superconducting material is in the order of 10 raised to minus 5. But the ratio of resistance of a material in the superconducting state to the resistance of the same material in the normal state is less than 10 raised to minus 5. It is called electrical resistance. When a superconducting material in the magnetic field, it becomes like a resistance current is from to continuously flow. Magnetic. Now the second superconducting property is the magnetic property. When the superconducting material are subject to a large value of magnetic field, its superconductivity is destroyed. The destruction of the superconducting property. The minimum field required to destroy the superconducting property is given by this formula: Hc is equal to H0 1 minus T square upon Tc square. In this formula, Tc is the critical temperature, H0 is the field required to destroy the superconductivity property at 0 Kelvin, and the Hc is the minimum field required to destroy the superconductivity at temperature T Kelvin. Now diamagnetic property. When a normal conducting material is placed, specimen is placed in the magnetic field, the magnetic lines is ejected from the superconducting material, and this effect is also called Meissner effect. This effect is found by the Meissner scientist, that's why it's called Meissner effect. On the other hand, if the materials is cooled for superconductivity, the magnetic lines of force ejected from the superconducting material. That's why figure shows that in normal material magnetic field B is present, but in superconducting material magnetic field B is 0. That's why the magnetic lines is ejected from the superconducting material, and it's called Meissner effect. First is observed by the scientist of Meissner. Now the second property is the effect of electric current. Now the application of large value of electric current to a superconducting material destroys the superconductivity. Consider a cool wire wound on a superconductor. This figure shows that one is the superconducting material and wound with the wire. The formula is the IC is equal to 2 pi r Hc. In this formula, Hc is the critical magnetic field and R is the radius of the superconducting material. Now the second thing is, let I be the current of flowing through the wire, and the application of the current induce a magnetic field. In when the induced magnetic field in the conductor destroys the superconducting property, the induced critical current required to destroy superconducting property. Now the next property is the effect of pressure. Certain in material are brought into the superconducting state by increasing the pressure. Example like a cesium is a normal conductor at atmosphere pressure. While increasing the pressure of cesium, it is converted into the superconducting material at 110 kilobar from normal material. Now second is the isotopic effect. Isotopic effect is the property of superconducting material is explained by the presence of isotope slightly changes the transition temperature of the superconducting material. The atomic mass of mercury varies from 199.5 to 203.5. Due to the variation atomic mass, the transition temperature of isotope of mercury varies from 4.185 to 4.146 Kelvin. Maxwell shows that the transition temperature is inversely proportional to the square of root of the atomic mass of the isotope of a single superconductor. Here, this is the formula of the isotopic effect. Tc is directly proportional to 1 upon m raised to alpha. Here, alpha is the constant value and m is the atomic weight of mercury or any superconducting material. Here, two types of superconducting material, type 1 and type 2 superconducting material. Type 1 superconducting material is also called as soft superconductors, and type 2 superconducting material is also called a hard superconductors. Now, first we explain about the type 1 superconducting material. Type 1 superconductors. Type 1 superconductors behaves as a perfect diamagnetic material and obey the Meissner effect, because the superconducting materials magnetization value is most probably negative. Then the diamagnetic material have also magnetization value is negative. That's why the type 1 superconductors behaves as a perfect diamagnetic material, and it's also obey the Meissner effect. Like type 1 superconducting material, when the specimen is applied a magnetic field, the magnetic lines is ejected from the specimen. Second point, relation between the magnetization produced and the applied magnetic field for type 1 superconductors. A negative sign is introduced in the magnetism value 2 represents the diamagnetic property of the superconductor. That's why type 1 superconductor is also called a perfect diamagnetic material. Here a graph of the type 1 superconducting material it shows that the HC is the magnetic field. Above HC is normal state, but HC is below. The material behaves like a superconducting state. The material produces a repulsive force up to the critical field HC penetrate through it. Hence, the material behaves as a superconductor. As an example, mercury, niobium, vanadium, that's all types of type 1 superconducting materials. Now, the second thing, type 2 superconducting materials means hard superconducting materials. Type 2 superconductors. Type 2 superconductors do not perfectly obey the Meissner effect. These materials behaves as a perfect superconductor up to Hc1. Above Hc1, the repulsive force decreases, resulting in decrease in the magnetism M, and hence the magnetic flux starts to penetrate through the material. Here the graph of the type 2 superconducting material, here two magnetic field Hc1 and Hc2. Hc1 and Hc2 and Hc. These are the vortex states or a mixed state. Now the second point is, above Hc1 the repulsive force decreases, resulting in decreases in the magnetism M, and hence the magnetic flux start to penetrate through the material. The magnetic field penetrates up to the value Hc2 in the region up to Hc2. The materials as a superconducting material, and it shows in this graph type 2 superconducting material. Nb3 Sn, Nb3 germanium, and Y123 that are examples of the type 2 superconducting material. Now, in this topic, important theory is the BCS theory. The photograph of the founder Bardeen, Cooper, and Schrieffer, and they got Nobel Prize in 1972 for this type of theory. Now, Bardeen, Cooper, and Schrieffer, it's the prove the BCS theory. The theory of superconductivity developed in several levels in 1957. Now, it explained phenomenon associated with the superconductivity in a natural manner. This theory involves the electron interaction and the phonon as a mediator. The main idea behind the BCS theory experimental results of the two effects, namely isotope effects, and the second one is the variation of specific heat with the temperatures. Main postulated of the BCS theory and the major accomplishment in 1950, Froelich and Bardeen, the existence of self-energy of electrons accomplished by virtual phonons moves through a crystal lattice. Now, what is phonon? Phonon means the lattice, crystal lattice is attraction of the electrons. It is called the phonons. Now, electrons traveling in a solid interaction with lattice vibration by the virtue of electrostatic force between them. Now, the oscillator distortion of the lattice is quantized in terms of the phonons. This interaction is called electron-phonon interaction, which leads to scattering of electrons and hence cause a change in the electrical resistivity. Generally, resistivity of metal is linearly increased with the temperature, but the superconductivity's resistivity is decreases with non-linearly temperatures at a room temperature. That's why the resistivity is the sensitive with temperature, particularly in the low temperature region, since the number of phonons increases with the temperature. Now, it's assumed from the BCS theory that the electron-phonon interaction produces an attractive interactions between the two electrons. Here is the figures of the electron-phonon interactions. Here in this figure, the K is the wave vector emits a virtual phonon which is absorbed by the another electrons. K is the scattered as K and minus Q and the plus Q. The resulting electron, the result is the electron-electron interactions depends on the relative magnitude of the energy change and phonon energy. Now, this theory is totally in quantum physics based theory. Once the phonon energy exceeds the electronics energy, the interaction becomes attractive interactions. Now, attractive interactions, the wave vector and spin, and the result is the electrons and the result is the attractive interactions. Now, what is Cooper pairs? The two electrons interacting attractively in the phonon field, it is called the Cooper pairs. Means two electrons pairs, it is also called the Cooper pairs. Now, the electron phonon, what is the electron phonon interaction? Electron charge repel each other with an interaction Vc, but BCS people assumed superconducting phase dominates over Vc. That's the equation here is the V is equal to Vph plus Vc is less than 0. The net interaction is the attractive interaction. The energy of the pair of electrons in the bond structure is less than in the free state, where the electron exits separately. The difference in the energy between the two states is known as binding energy of the Cooper pair. The electron lattice electron interaction is stronger than the electron Coulomb interaction when the temperature is less than critical temperature. That's why the net interaction is the attractive interaction, and this is the funda of the BCS theory. Now, the Cooper pairs is completed at T is equal to 0 Kelvin and is completely broken when